Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on probability, lecture number 14, in which I will prove some theorems and solve some problems on independent events. Now we prove a theorem. Theorem is if A and B are two independent events, then so are events A and B prime. B prime be the complement of B. Now we prove this. Since given that A and B are two independent events for a sample space S, then for the condition of independent events, we know that probability of A intersect B equal to probability of A multiply probability of B. This is number one. Now we see this picture. Here we see that this rectangle is sample space S and this circle is event A, this circle is event B. Therefore, the portion for complement of B will be the dotted portions, because this dotted portion is the portion except the event B, and this dotted portion is complement of B. Now we come to the next figure. Here this dotted portion is the common place between A and complement of B. That means this dotted portion is A intersect complement of B. Now here, next figure. Here this dotted portion is common place between the event A and event B. So this portion is A intersect B. Now we come to the next figure, this figure. Here this part is A intersect B complement and this part is A intersect B. Now we see that A intersect B complement means A intersect complement of B, this portion, and this portion A intersect B are mutually exclusive. That is, A intersect complement of B intersect A intersect B equal to null set phi. This is number 2. Again, union of these two portions make the set A. Since set A equal to A intersect complement of B union A intersect B, probability of A equal to probability of A intersect complement of B union A intersect B implies that PA, here A intersect complement of B and A intersect B are mutually exclusive. Therefore, we may write this as probability of A intersect complement of B plus probability of A intersect B. implies that PA intersect complement of B equal to PA minus PA intersect B, implies that probability of A intersect complement of B equal to PA probability of A minus, here using 1, probability of A multiply probability of B, since A and B are independent events, using 1, implies that probability of A intersect complement of B equal to common PA, here 1 minus probability of B, and this equal to PA probability of A 1 minus PB, means probability of complement of B. Here we see that probability of A intersect complement of B equal to probability of A multiply probability of complement of B. Therefore, A and complement of B are independent events. Proved. Now we prove theorem 2. This theorem is if A and B are two independent events, then so are events A prime and B. Similar to theorem 1, we may prove this very easily. Here, given that A and B are two independent events for a sample space S, then PA intersect B equal to PA multiply PB. This is the condition for two independent events A and B. This is number 1. Let this rectangle is sample space S and this circle is event A and this circle is event B. Then dotted portion be the portion except event A, that is the dotted portion is complement of A. Here this dotted portion is common place between B and complement of A, that is this dotted portion is complement of A intersect B. Here this dotted portion is the common place between event A and B. So this dotted portion is A intersect B. So here this portion in this figure, this portion is A intersect B and this portion is complement of A intersect B. Now here we see that complement of A intersect B and A intersect B are two mutually exclusive events. Therefore, their intersection will be phi. Here we see that B equal to complement of A intersect B, this portion union this portion A intersect B. We write P both sides probability. Here in right side we see that this event and this event are mutually exclusive. Therefore, this probability will be equal to probability of complement of A intersect B plus probability of A intersect B. Now we write this in left side. Then in right side we get probability of B minus probability of A intersect B. Since A and B are independent events. Therefore, probability of A intersect B equal to probability of A multiply probability of B using 1. Now, here we take common probability of B. Here remains 1 minus probability of A. 1 minus probability of A is probability of complement of A. So, this is equal to probability of B multiply probability of complement of A. We may write this probability of complement of A multiply probability of B. Therefore, we get probability of complement of A intersect B equal to probability of complement of A multiply probability of B. Therefore, complement of A and B are independent events. Proved. Now we prove the next theorem. If A and B are two independent events, then so are events complement of A and complement of B. Now we prove this. Given that A and B are two independent events, therefore from the condition for two independent events, probability of A intersect B equal to probability of A multiply probability of B. This is number 1. Now we see this figure. Here first circle is event A and second circle is event B. The dotted portion B, the event A union B. And in the next picture, the dotted portion is except portion A union B. That means this dotted portion B complement of A union B. Here we see that in both pictures, this dotted portion and this dotted portion are mutually exclusive, means intersection will be phi, and these two dotted portions make S by their union. Therefore, since A union B and A union B complement are mutually exclusive. Therefore, A union B intersect complement of A union B equal to phi. This is number 2. Again, S equal to sample space S equal to A union B union complement of A union B implies that we write probability in both sides. PS equal to P A union B union A union B complement. Since this event A union B and complement of A union B are mutually exclusive, therefore this will be equal to P A union B plus P A union B whole complement. Since PS probability of sample space is always 1, this is 1 and this is P A union B plus P A union B whole complement implies that P A union B whole complement equal to 1 minus P A union B. by De Morgan's law, here P complement of A intersect complement of B, and right side is 1 minus P A union B by De Morgan's law. Implies that P complement of A intersect complement of B equal to 1 minus. This means PA by total probability PA plus PB minus PA intersect B, and this will be equal to 1 minus PA minus PB minus minus plus PA intersect B. This equal to 1 minus PA means complement of A, probability of complement of A, minus PB. Here A and B are independent events. Therefore, using 1, we get here PA multiply PB. Using 1. This equal to P complement of A. Here we take common PB. 1 minus PA. This equal to P complement of A minus PB. Here 1 minus PA means P complement of A. We take common P complement of A 1 minus PB, and this equal to P complement of A 1 minus PB is P complement of B. Therefore, P complement of A intersect complement of B equal to P complement of A multiply P complement of B. This means complement of A and complement of B are independent events. Proved. Now we prove the next theorem. Next theorem is known as complementation rule. Here statement is, if A and B are two independent events, then the probability of at least one of A and B is 1 minus probability of complement of A multiply probability of complement of B. Now we prove this. Given that A and B are independent events, therefore from the condition of independent events, probability of A intersect B equal to probability of A multiply probability of B. This is number 1. Here probability of at least one of A and B equal to probability of A union B. Probability of A union B is probability of A by total probability plus probability of B minus probability of A intersect B. This equal to probability of A plus probability of B minus, here A and B are independent events. So using 1, this equal to PA multiply PB. Using 1. And probability of A may be written as 1 minus probability of complement of A. Here we may take common probability of B. Here 1 minus probability of A. This is equal to 1 minus probability of complement of A plus probability of B. 1 minus probability of A is probability of complement of A. This is equal to 1 minus, we take common P complement of A. Here 1 minus PB. This is equal to 1 minus P complement of A, and 1 minus PB is P complement of B, and proved. Now we solve a problem. Problem is, if probability of A equal to 3 by 5, probability of B equal to 1 by 5, then find probability of A union B if A and B are independent events. Since we know that P A union B equal to P A plus PB minus P A intersect B, and PA is 3 by 5, PB is 1 by 5. Since A and B are independent events, therefore PA intersect B equal to PA multiply PB, and this equal to 3 by 5 plus 1 by 5 minus PA 3 by 5, PB 1 by 5, and this will be equal to 25 LCM. Here 15 plus 5 minus 3 means 17 by 25. In another process we may solve also another process. Since we know that P A union B equal to 1 minus P complement of A, P complement of B if A and B are independent events. This rule is for complementation rule, and this equal to 1 minus P complement of A means 1 minus PA, P complement of B means 1 minus PB. This equal to 1 minus PA means 1 minus 3 by 5, 1 minus 1 by 5. This equal to 1 minus, this is 2 by 5 multiply here 4 by 5 means 1 minus 8 by 25, and this is equal to 17 by 25. Same result in both process. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.